Back. All right, today we're going to talk about stochastic simulation. This is interesting because lots of problems that we're going to look at for the rest of the course are going to be much bigger than we can solve exactly. We'd like to solve them approximately, and stochastic simulation is one of the ways of doing this. So we can do probabilistic inference in the models that we've seen, but by sampling. Okay, so that's why we're going to do this, because some problems are just too big. All right, so the idea is we can go from probabilities to and from samples. And so here's an example. If we have some variable x that has k different values and we have this count, we can use the empirical probabilities as a probability, or we could use something like Laplace smoothing. We get the probabilities. So we can go from counts, we get probabilities, but from probabilities we can also get counts. So if we know the probability distribution, what we can do is to sample and to try to get out a whole lot of, we can try to generate m samples from this, which have that probability. So that's what we're going to try to do here. So the idea is if we could sample from a variable's posterior probability, we could estimate its posterior probability. So if we can sample, then we can estimate probabilities. And often we want to make decisions. It's useful to be able to just estimate a probability. We don't actually need it exactly. We just want to estimate it often. Okay, so we're going to think about sampling and then using that to estimate probabilities. All right, so here's the idea before a one-dimensional real domain. So it can be a discrete domain or a one-dimensional real domain. So it's only for one dimensions. First of all, we're going to totally order the values in the variable in the domain of x. So if it's a real valued variable, it's pretty ordered. It's already totally ordered. Otherwise, we're just going to pick some arbitrary ordering. Doesn't really matter what ordering it is for discrete domain. And for a real one, you might as well just use the normal ordering of the real numbers. Then we generate what's called the cumulative probability distribution, where f of x is the probability that the variable x has a value less than or equal to the x. So it's the probability so f of some number is the probability that x is less than or equal to that number. All right, it'll make sense in a second when we give an example. Then we're going to select the variable y uniform in the range of 0 to 1. So we're going to just select the normal random number generator in a computer, selects a value uniform in the range 0 to 1. And then we're going to select the x such that f of x equals y. And then that is going to be distributed the probability according to this probability p. So here's this idea. So here's p of x on the left. And suppose the probability of v1 is 0.3, the probability of v2 is 0.4, the probability of v3 is 0.1, and the probability of v4 is 0.2. Now we drew the cumulative distribution. So we're going to go from, we're totally ordering it so that 0.3 is the probability that it's equal to v1, right? And the probability it's v1 or v2 is goes up to 0.3 plus 0.4 is 0.7. So it goes across there and up there. Then similarly for v3, the probability is v3 or v2 or v1 is 0.3 plus 0.4 plus 0.1 is 0.8. And v4 is just the rest of it. So now what you want to do is now we want to just pick a number at random. We're going to just pick numbers at random on this y-axis of here. And notice that with probability 0.3, it's going to hit this bar here, and that is exactly equal to the probability of v1. 40% of the time, it's going to hit this one over here, which is it's going to give a v2. 10% of the time, it's going to give a v3, and 20% of the time, it's going to give a v4. But that's exactly the probability distribution of p of x. Okay, so if we just generate this cumulative distribution and pick random numbers for y, we're going to pick according to that distribution. And we can do that if we can do it for a normal distribution or any one-dimensional distribution. It, however, doesn't work for multi-dimensional distributions. We have to do something different. But before we look at that, let's look at some theoretical properties that are interesting. Okay, you don't remember this, but it's interesting. So here's a theorem from Hoeffding. You might have studied this in statistics courses. We're only using it now because it tells us interesting things. We're going to apply this to what we're doing. Suppose P is the true probability, and we're going to generate samples. And S is the sample average from n samples. And Hoeffding's inequality says the probability that your error is bigger than epsilon has this funny form here. Don't worry about what it says. But what we want to do is to get what's called a probabilistically approximately correct estimate of the probability. So we want one that's probably approximately correct. All right. And so what we're going to do is if you're willing to have an error greater than epsilon, so this is my error, in less than delta of the time, you might want an error of 0.1 and less than, an error bigger than 0.1 in, less than 10% of the cases. We're going to solve this, it's got to be less than delta. And we're going to solve this for n, so this way it's because we want this probability bigger than epsilon has to be less than delta. And you can now solve it for n. And you get this. Don't worry about it, what it says here. But what's interesting for us is this table. So if we want an error of 0.1, okay, so if you want to be with this one significant digit, and you wanted to do this 95% of the time, right, you need 185 samples. So 185 samples is enough samples in order to just be one significant digit. If you want to get epsilon to be 0.01, you want it to accurate to two significant digits, and you want to do it 95% of the time, which is what this says, you need a lot of samples. We need 18,445. But this is within 2 digits of accuracy, right? So we're discriminating here within 2 digits of accuracy. If you want to do 1 digit of accuracy, but you've got to do it 99% of the time, so it's very unlikely going to be wrong, well, we need a few more than that. We need 256. So we're sort of going to look at this. We're going to think about what we're going to do. We're going to use a few hundreds or maybe 1,000 samples, and it's really only one significant digit that we're going to use here, and it's going to be pretty accurate, right? So, you don't want to look beyond, if we don't have this many samples, we don't want to look beyond 2 significant digits. It's just one significant digit or maybe, not quite 2 significant digits. So you shouldn't do that accuracy. So that's how we're going to view this. But the point is it depends on the number of samples that we have, and that's going to be important in the middle. So the complexity here depends on the number of samples that we have, and it's going to be easy to get within one significant digit. We're going to need a lot more samples in order to be accurate enough to 2 significant digits. All right. So now we have to think about what happens if you have multiple random variables that are not just a single linear random variable. This is what we can do. Here's the first idea is we can do forward sampling in a belief network. So what we're going to do is we're going to sample the variables one at a time. So we're going to generate lots of samples, but we're going to generate the samples one at a time, and we're going to make sure we sample the parents of x before we sample x. But now given values for the parents of a variable x, right? The probability of x given its parents is just a normal one-dimensional dimension. We know how to do this, right? This is the probability of x given its parents. We know how to sample from that distribution because that's just a normal one-dimensional distribution. We've already seen that. So given the values now, given the values of the parents, we're going to sample x from the probability of this. And that's now easy to do. We know how to do that. Okay, and that's all that happens here. All right. But it's not very interesting, right? This just gives the probability of all the variables in a sample. What we typically want to do is to use the posterior probability. You want evidence. So what we'd like to do is to estimate the posterior probability of some variable given evidence. So we'd like the posterior probability given the evidence, say y1 equals v1 and yj equals vj. All we're going to do is to reject any of the samples that assign yi to a different value. So they're all just rejected. And it turns out that the non-rejected samples are distributed according to the posterior probability. And now we're going to do the probability of any alpha given evidence is we're just going to do the proportion of the samples where alpha is true. So all this says is we're just summing over all the examples where alpha is true. That's all that funny symbol means. And this says just the number of examples, the number of samples, over here, just dividing it by the number of samples remaining, because we rejected lots of them, right? We rejected them. Okay, so we only consider the samples consistent with the evidence. And this then gives us a posterior distribution. So let's look at how this works. This is our familiar example we did before, the probability of tampering, fire, alarm, and report. And suppose we observe smoke is true and report is true. So we observe smoke and report. Okay, we generate one sample by random chance. Tampering is false, and fire is true, and alarm is false, and smoke is true, and leaving is false, and report is false. And now we're going to see, should we accept or reject this? Okay, and if we look at this, the report here is false. We've observed it to be true. So we observed it to be true, but this sample is false. We're going to reject this sample. This sample is rejected. It's no longer considered. Suppose we have this sample. We're going to make sure that what we want to do is we have smoke is true and report is true. So we're going to keep this sample, right? We're going to keep this sample. And if we have a sample true, false, we've got to smoke is false, then we're going to reject this sample. We don't even need to continue here. We can reject it. We can reject things quickly before we've generated all the variables. So we're going to reject this. And so far, and then we're going to go on, and this is true. We're going to check here where smoke is true and report is true. So we're going to keep this one. Okay, so we're going to, and then we're going to do 1,000 samples, for example. Okay, and what we expect to do is the proportion of those with tampering is true corresponds exactly to the probability of tampering, or approximately the probability of tampering. The proportion of these where fire is true corresponds to the probability of tampering. The proportion of those where smoke is true corresponds to the probability of smoke. Okay, and that's just approximation, and we can use Hoeffding's inequality. We'll see that it's very good for one significant digit, and it gets okay but lots of errors for two significant digits. Okay, if we consider the probability of smoke is 0.02 and the probability of report given 0.03, and there are 1,000 samples, how many samples are rejected? So think about how many samples are rejected and how many examples are used. Okay, think about that in order to do, and we'll talk about this in class. And it turns out this doesn't work very well when evidence is unlikely, and by thinking about how many samples rejected and used, you can work out what's going on here, because you can actually apply Hoeffding's equality to the number of samples that are actually used. Okay, let's stop there for now. Thank you.